Okay, well, we'll talk about the space news, December 11th. Start right off with one of the big ones, which is an asteroid mission called DART, which stands for Double Asteroid Redirection Test. The double asteroid comes from the fact that it's two asteroids, the larger one called Didymos, and there's a smaller one, which is the one we're actually going to hit. The purpose of this mission is really to test planetary defenses. We always talked about it, that we want to divert asteroids that might be on a course with Earth. And these aren't, but they're close enough that we can practice on them. So this is really a first demonstration of doing this sort of thing. So the one we're aiming for is the smaller one there, 535 feet in diameter, which actually is probably pretty typical of a lot of the ones that are thought to possibly threaten Earth. The current projections are that as far as we know, maybe the next 100 years, we're probably okay, nothing in the way, but also it's pretty universally agreed that we probably only identified maybe 30 or 40% of all the ones out there. So there's still, even in the next 100 years, you might need to defend something like this. The mission is called DART. It just got launched on November 24th. And the idea is alter the orbit, meaning to push it a little bit. The idea is normally if you do it way, way ahead of time, you don't have to push it very much. And of course, that'll solve the problem. It'll get there. Actually, it takes about a year, September 2022. The craft itself weighs about 1,100 pounds. It'll slam into it about 15,000 miles an hour. So it's kinetic energy, just basically trying to divert it. And what the hope is, it'll change the orbital period. It'll be easy to measure it because because it orbits around the larger one there, it'll be easy to measure the period. You'll be able to really know pretty well how it did. Now, additionally, you'd kind of like to know, what does it really do? You never quite know the composition of these asteroids. I mean, some of the ones we've gone through recently turned out to be a lot softer than we expected. I mean, maybe you just blast through it. So as a follow-up mission, the European Space Agency in 2024 is going to launch a separate mission called Hera, which will be studying the effects. So it'll be launched in 2024. It'll get there around 2027. So it'll take a while to get all the results of this, but at least we'll know about the orbit effect. We'll know about that one fairly soon. So anyway, this is really the first time there will be a measurable impact on the orbit of a planetary body. I mean, you could say, yeah, every time we crash something into the moon, we alter a little bit, but nobody could measure that. It's too small. This will actually be noticeable. It may produce a meteor shower. You're going to throw up a bunch of stuff off the surface, again, depending on what it's actually made of. We may be able to see that. A few of those might even actually hit Earth's atmosphere. They don't really know. But that's all speculation. Now, this particular mission, they had a couple interesting things. One of them is there's a very small follow-on, this Lichia cube. It's a small CubeSat. It's about 10 CubeSat units, where they're 4-inch cubes, so it's the size of 4 10-inch cubes. It's ejected well before we get in distance to strike Dimorphos there. It's ejected so they can take pictures. I mean, after all, once the thing is smashed into it, you won't get any more pictures. So there's a separate little mission for that. So that thing, it weighs about 31 pounds as opposed to the 1,100 pounds, of the basic craft. Interesting other things that are being tested out on this mission. One of them is the solar cells that are on this. You can see the arrays there. They're about 60 feet wing to wing there is about the size of those things. They're doing the rollout solar cells. They come, they all wrapped up a cylinder, and then they expand on them. That's what was done on the space station recently. The most recent solar arrays installed there, we're done with that. And so now they're trying it on a planetary spacecraft. So that's a little different. They also they're trying some new kind of solar cells where they have a lot more reflection. Basically, they focus a lot more of the light just with some kind of reflectors on the solar cells. The whole thing is not made of that, but some of it is, so they're testing that out. And the other thing is they have a new ion engine. This is by far the most powerful ion, electric propulsion engine that's out there right now. And they're not really using that to get there. It's really just for test purposes. Yeah, on the way there, they're gonna run it for a while just to make sure it works. But really, there's 12 hydrazine thrusters, more typical traditional kind of thrusters that are used for actually getting most of the way there. And in particular, for the last-minute course corrections, you need something more powerful than an ion engine for course correction at the end.
Those ion engines normally have to thrust the force of about one sheet of paper.
Oh, this is a lot more than that. It's the last time they sent one of these up was for the mission to Ceres, and this is 3 times more powerful. I think it measured in like millinewtons, it's like 200 something, as opposed to like maybe the 20 or something around a lot of the satellites. Most new satellites all have ion thrusters as well. They're just a lot smaller. This just happens to be bigger. So there's still nothing compared to a traditional thruster. But the idea is they can be on continuously, and then the cumulative effect could be, pretty dramatic, and they're fast. Yeah. This one is xenon, unlike the krypton that they're using, for instance, on the Starlink satellites. What was that? Oh, okay, yeah, this is using xenon. But this is version C of this engine. They've had previous ones before, so it's just continuing. And for those who don't know, an ion engine is really pretty simple. They basically just you ionize the gas, which is xenon or whatever it's going to be, and you just have you have a screen you electrify, and the ions go shooting toward it, and they end up going about 90,000 miles an hour, and they shoot through it, and that's your propulsion. So it doesn't, you are emitting some particles, but it's nowhere near as much as you would get, or as much as you would need with traditional thrusters. Okay, one question you might have asked, maybe not, but maybe you might have asked, is how do all those pictures that they're taking of this asteroid, how do they get back? And in general, especially you think about it like all those really long distance probes like Voyager and that sort of thing, they're still communicating. How do they do that? Well, it's a deep space network, and that's how they get there. It's actually just 3 sites on Earth. Each of them have 4 or more antennas. They're 120 degrees apart in latitude, so that no matter what time of the day it is, there's at least one antenna that'll be able to look out and see things. So you have 100% visibility once you're like 30,000 miles or something away from the Earth anyway. The sites are in California, near Madrid, and near Canberra, Australia. Those are where they are. They all have at least 4 antennas. Each one has one large antenna, which is 70 meters, about 230 feet. That's what's pictured in this picture here, which has about an acre of surface area. What's interesting, though, is that really they're also doing a lot more of tying in with lots of other antennas all over the place. That way, they get basically, you can get a lot more sensitivity by tying in additional ones. You can imagine, you're adding in signals from two different places. The signal you're looking for is going to get added together, and the ones you're not looking for are just kind of random and kind of cancel each other out. So the more antennas you have, the better off you are. But even given that, you're looking for very, very small signals. And what I found in one source was the signals, by the time you get to the outer planets, way beyond the asteroid belt, but the outer planets like Neptune, the signal is 20 billion times weaker than the power that runs your digital watch. So you're looking at a very, very small amount of power. Somehow it has to be received. Well, amplifiers, typically all electrical equipment has a lot of noise. And so what they do is to reduce that, they cool the amplifiers down to a couple degrees above absolute zero. So it's fairly exotic amplifiers. The actual antennas haven't changed that much in the last 15, 20 years probably. But the signal processing in particular is what's better now. They're much better at that, and in particular, combining the outputs from multiple antennas. So what are they used for in general? Obviously, they're listening, but of course, they're also sending. They're transmitting commands. If you're going to tell the craft it's time to initiate a landing sequence or whatever it's going to be, they have to do that. And I should have mentioned, they are operated by the Jet Propulsion Laboratory. They've been running since 1958, and they've supported everything. The Voyager, which is going way, way out there. We also support US, Europe, Japan, and India, almost everybody but China. Well, I guess, and Russia.
Why are the amplifiers cooled to a few degrees? Like, does that somehow?
Yeah, that's just electronic devices. The more the molecules vibrate in the equipment, the more noise.
I have a question. Should I get off the DART satellite?
Yeah.
So since they're planning to impact asteroids, were they designed it structurally differently? Like, is it meant to instead of breaking apart, maybe stay together a little bit?
I don't think they really care, as long as the more it holds together, the better, I guess, it doesn't go flying off. If you look at the thing, it was kind of square, but that really is just because nobody cared about air resistance. But
my understanding is that they likened it to shooting a vending machine. They're going to shoot a vending machine at 15,000 miles per hour into the asteroid to see what happens.
Yeah,
because that's about the size and shape of it.
Yeah, they expect a crater maybe 20 miles or something, but again, they don't really know, because they don't really know the composition of this thing. They don't really even have a good picture of it yet. So,
Wow.
The pictures they have are all pretty fuzzy.
Right, you can appreciate if it's made of something the consistency of frozen cotton candy, that impactor is going to go real deep.
Yeah.
Whereas if it's more of a stony composition, the impactor will only hit and maybe like sort of bounce off or leave a very small crater. So it's going to be somewhere in between those two extremes, most likely.
Yeah, that one recent asteroid sample return project, the American one, that one, they were surprised at how soft it was. They expected just barely scratch the surface and everything just kind of went right in. And so they don't really know. And they're probably all different. There's no guarantee that they're all the same size or the same texture. Okay, so moving on, that particular 70-meter dish that happens to be in California, but they all look pretty similar, except maybe they have more greenery around them. Okay, the next one is talking about debris in orbit, in this case caused by the Russians with their anti-satellite missile tests. So there's a lot of acronyms that come up, especially if you get government or military things involved. So ASAT stands for anti-satellite weapon. This is a DA ASAT. DA means direct ascent, means comes from the ground. So what happened is the Russians, there's lots of old dead satellites up there that nobody can do anything with anyway. They had an old one from decades ago that weighed about 2 tons. So it was a pretty good sized satellite. And so they launched missiles at it. Now, the missiles, they probably were actually from tubes in the ground, but they're really just derived from what you see on the picture on the left-hand side there. They're basically something that could be done from a mobile launcher. And that particular one, nobody really knows about it, what it looks like that much, but the company in Russia that builds this stuff for the government, which was called Almaz Antef, they put out a corporate calendar in 2015 and they had that picture on it. So that's where that came from. So somebody noticed this and that's how I picked up that picture. So thank you for corporate calendars. Anyway, they come in handy. The point is, it can be launched from a mobile platform. It's, these things aren't necessarily that huge. So the satellite that was up there was about 300 miles up, which is low Earth orbit. That puts it about 20 miles or 40 miles higher than the International Space Station. So it's in that same kind of range. There's an awful lot of satellites in that area, at that altitude. They don't need to have an explosive warhead. This particular missile can, because in the early days of anti-ballistic missile defense, even the Russians weren't that confident they could actually hit an incoming missile. So they figured if they put a nuclear weapon in it, they could blow it up and they'll take care of anything in the vicinity. So they could actually be armed, but that's not necessary if you're just taking out a satellite, as long as you're confident that you can hit it, which they were, and which they proved they can. Because this is just a variant of their anti-ballistic missiles system. Essentially the same missile. They have several variants of them. So when they destroyed the satellite, they were demonstrating, one, that they can destroy a satellite, but they're also demonstrating their anti-ballistic missile capability too. They're doing both of those things. Now, one point about these things, it only takes 5 or 10 minutes for it to get up there. So there's not a lot of time to react if somebody launches an attack on a satellite. So everybody in the military is saying, yeah, we've got to pretty much figure an autonomous reaction. Whatever is going to happen has to happen almost automatically. There's not time to go and call a meeting and page people and wake them up and get permissions to do whatever they're going to do. It's going to happen automatically.
Which is needed.
Yeah. Well, that's what they're saying. That's all essentially the same stuff. So yeah. Okay. Now, of course, the really bad downside of all this, besides any military issues, is debris, and it's just a constant issue. There have been several tests in the past that caused debris. Actually, back in 2007, 2008, the United States did one, and Russia did one around then too, actually, as did India, interestingly enough. They even did them. In those tests, actually, there were smaller satellites that were attacked, and they were in lower orbits. Lower orbits are good because things decay pretty quickly. You have air friction, and anything in orbit below this kind of an altitude, and get down to a couple hundred miles, chances are those things will only stay in orbit 5 years or so. So the problem is sort of kind of self-correcting for low orbits, but the higher up you get, there's less and less, there's fewer air molecules, and the fewer you have, the longer it lasts. So even just going up to 260, going up to maybe 300 miles, you're already at the point where stuff will stay around for decades. So in this particular case, when they impacted it, it created about 1,500 pieces of trackable, easily trackable debris. And easily trackable is classified as about 4 inches or bigger in size. There's probably hundreds of thousands of pieces of smaller debris. And the reality is, I think we could track some of that too, but it's probably classified and we don't see it all. One interesting thing about this test, one, it was the satellite was heavier than a typical one in the past. But two, usually you kind of go for a head-on collision. You want to have as big a velocity difference between your interceptor and the satellite itself. You get more kinetic energy used. This case, they actually partially matched the orbit. So what they said is actually, even though they didn't get a head-on collision, they still had enough of an impact that they could destroy it pretty easily. But the really bad thing about this one is that because it was essentially coming in, kind of going in the same direction, you basically, on the whole, on average, you added kinetic energy to all those particles as opposed to subtracting by the collision. And as a result of that, most of the debris went higher. It got more energy, the orbits go up higher. So that means it'll be around even longer. So that was especially annoying that way. And dangerous, really, in the case of a lot of satellites. We're going to be threatened for years. Actually, the Chinese test in 2007 was kind of like this. There's still debris floating around up there that people are dodging here and there. That happens all the time. But the debris from this particular collision is 190 to 680 miles from what they know so far. And the lower orbits, like I said, 5 years, it'll probably clear itself out. But it'll be decades before the other stuff clears itself out. Now, this picture on the right-hand side, this was kind of a simulation, but this is showing what the impact looked like. Every one of those little red dots indicated a major piece of that spacecraft. And this was probably simulated like minutes. Yeah, I'm not sure the exact time scale here, but maybe minutes after the collision. Now you can imagine over time, they spread out. They actually all have, velocity in 3 different directions. They're going to be going, outward and upward and downward and left and right. So that cloud will get bigger and bigger over time. But that was even fairly quickly, you cover a pretty big area. This did have a fairly immediate impact. International Space Station, they actually kind of went through a shutdown mode where the astronauts, including the Russian astronauts, everybody had to get in their spacesuits, get in their crew capsules. They closed all the hatches in between all the different modules of the space station. And it turned out nothing happened. They were okay, but they weren't sure. There was enough risk to that. And also, apparently, SpaceX had to adjust the orbits of some of their Starlink satellites as well. So, already it's had an impact. I think even the Chinese space station, they got worried a little bit, but apparently didn't have any impact yet. Little follow-up on that. There supposedly was a threat directly issued on Russian TV, Channel 1 TV, where they threatened to blow up, right after this test, they threatened to blow up 32 GPS satellites, quote, if NATO crosses our red line. And they were saying then rendering the GPS guided missiles useless. Now, if GPS actually did go up, that would be pretty serious, not only for commercial stuff, but for military as well. We do rely on it a lot. Although the military does have backup systems to some extent. Presumably the red line they're talking about was when they invaded the Ukraine, doing anything about that. But there's some reason to doubt that this was really a serious threat. And the main reason is that the GPS satellites are up a lot higher. They're up about 12,000 miles. That's medium Earth orbit. But that missile that's used, that they launched, no one's ever seen it go even as high as this before. But even that was, the range is thought to be maybe 1,200 miles or so. Nowhere close to the other one. Now, of course, that's not to say that in the future they won't make them more powerful. But right now, it probably is not that much of a threat. And it's also a little suspicious. There's one obscure website that actually started this, and it got picked up there. Could be just fake news, or more likely propaganda, or just maybe a badly informed TV host. We don't really believe everything we see on our TV either, so not much reason to believe Russian TV in any case. But despite all that, the test, the fact that it existed, that pretty much is the message itself. It's sort of saying they can do this. That's their intention, and you can bet that on the whole, they're going to be trying to expand their capabilities. And if you want people that want to take out satellites at higher altitudes, they can do it now. There are satellites up there that they can just crash together. They can have ground-based lasers. A lot of this stuff is already, we talked about this on the previous news sessions. The other thing is that GPS, it is vulnerable. And there is a lot of activity going on to try to make it more invulnerable, including, as we talked about last month, having some GPS capability off of Starlink satellites. The military has its own constellation of 120 or so satellites that they're going to have their own GPS. So, and every other country is doing the same thing. China already has their own, for instance. I think the Russians do too. Okay, moving on.
Before we move on, I did
Yeah.
have wanted to get your thoughts. It seems like destroying the satellites is one thing and pretty bad, but it seems like the long-term risk is the debris. Do you see a situation where we create a system that we're like protecting everybody's satellites just to prevent debris?
Well, obviously there's a lot of talk about that. Nobody quite knows what to do. I mean, maybe Russia. I mean, Russia figures most of the satellites going up aren't theirs, and maybe they don't care that much. But yeah, there is a question what to do. You can't really defend every satellite, especially the small ones. I mean, those really big ones that are out there in geosynchronous orbit, yeah, they're going to protect those pretty well. But every little 100-pound satellite out there, you just really can't do it.
You briefly mentioned Kessler cascade.
Yeah, I guess because we talked about that last time. But yeah, the general concern is the so-called Kessler cascade, where there's an explosion of some sort. It sends debris everywhere. That impacts others. They start crashing into each other and blowing up and creating more debris. The blowing up thing is actually a pretty real issue because there's not just satellites up there. There's also a lot of upper stages of rockets that didn't actually use up all their fuel. They're still up there, and every now and then they actually just explode on their own. That happens. So it's a definite risk. Again, the good thing is that most of this stuff is low Earth orbit, where at least it'll clear itself out. 5-10 years in the worst case. It's really the stuff that goes up higher that you worry about a whole lot more, because that could stay. You get up like those geosynchronous ones, they're essentially up there forever. But even the medium Earth orbits, you're probably talking tens of thousands of years when they could remain up there. So,
correct me if I'm wrong. The true horror of a Kessler cascade effect would be that the Earth would become surrounded by essentially a global minefield of metal components moving in every which direction at every which speed, and we would be unable to leave the planet safely.
Yeah, for quite a while.
Yeah, for quite a long time.
Yeah. And that's right. There are some projects on cleaning up orbital debris, and we've talked about some of those in some of the previous sessions too. But there aren't really a lot of good solutions for massive cleanups of small parts. Mostly it's oriented toward, for instance, the astro scale solution is you put a special plate on every satellite, and then when it's at the end of its life, something else comes along and attaches to that specialized plate. Okay, that's not going to work that well. But there certainly are projects. It is a concern, and things like this Russian test, just bring it to the forefront once again. Okay, moving on to NASA kind of issues. They have now officially delayed the target lunar landing, human lunar landing, to 2025. So I don't know. You're going to have to change the dates on your project, I guess.
Yeah,
you got at least another year.
I started talking about orbiting the moon.
Okay.
That's
how about just doing stuff related to the moon? Yeah. And by the way, so they said 2025, but they're not really exactly saying it's guaranteed 2025 either. They're just basically saying it'll be 2025 or later. So they're really acknowledging it was maybe unreal. It was probably unrealistic to begin with, but now at least they're admitting it. Now there's lots of easy scapegoats here. The Blue Origin lawsuit, NASA particularly highlighted that because that caused an obvious 7 months delay of sorts. Now the reality is that didn't stop people working on SLS. It didn't stop people working on Starship. So the reality was a lot of work was continuing anyway, but still it's kind of convenient to be able to blame someone. And the Blue Origin lawsuit, it did mean that, for instance, SpaceX could not talk to NASA during that period. And that had to slow things down, for the human landing system, which they're contracted to do. And of course, COVID delays, there was some storm damage, all those kind of things. And there's others that have already been identified about spacesuits, for instance. I mean, actually, somebody in NASA said that, no, we can't really get there because of the availability of spacesuits. We don't have them yet. And that's probably going to get worked. But obviously, there could be delays in space launch system. There could be delays in the SpaceX Starship, which does the landing on the moon. And for that matter, the in-orbit refueling. That's actually built into the schedule now because that's going to be required for the Starship portion of this. The Orion capsule, which is the human capsule that's in the current solution. All these things, could get delayed. By the way, the Orion capsule, They just revised the cost estimates on that. It used to be 6.7 billion. It's now going to 9.3 billion. So this thing, despite the fact that it's a, essentially a remade Apollo capsule, through the years, it gets modified slightly and made a lot more expensive.
I have an engineer from the Orion program come next month for a Q&A session. So maybe you can provide some insight.
Yeah, we'll try to avoid insulting him outright. But it's certainly a fair question, is why is it taking so long and costing so much? Some other notable things going on in some of the same announcements, they did officially commit that there will be an uncrewed landing of the human landing system, meaning the SpaceX or the Starship would make a landing. Now, actually, SpaceX had committed to that back when they got this, but it was never really officially stated by NASA that would be a part of the plan. Now it is a part of the plan. But NASA also said, oh, and by the way, the Chinese may get there first anyway. So that was not all good news. Other news that's NASA related, they've more or less really doubled down on the space launch system at this point. They've issued a contract to Northrop Grumman for $3.2 billion. And they're going to produce the solid rocket booster pairs for 6 more. Now, if you do the math on that, that says that each one of those is $500 million. So each launch, people have been haggling over what's the cost of an SLS launch. Well, it's guaranteed to be at least 500 million because that's what it costs just for those boosters. That's the SLS rocket on the right-hand side of the picture there. The solid boosters, they come in pairs, and there's 2 of them there. Those, by the way, if you look at them, if you look back at the NASA pictures from Space Shuttle days, they look exactly the same. The one difference is they are longer. They have an extra segment. They used to have 4 main segments. These are solid rocket boosters. Now they're 5. I mean, they are changing them some. They needed more thrust for a longer period of time.
Do they still have the parachutes? Do they recover the casing still? Or?
Well, they're actually. Well, they're not recovered. They're still reusing the ones that NASA had stockpiled earlier. This is sort of a typical NASA or maybe a typical government strategy. If you can't make an official decision for one reason or another. What you do a lot of other stuff like this, where here you committed that you're paying ahead the next 10 years just for this little part of the program. But that kind of locks you in, because then you say, oh, we've already spent all this money. We better just keep going doing this. This is essentially committing us for the next 10 years. So anyway, the point is the Artemis 1 through 3 launches, which are the first 3 launches to the moon. The first one just goes around the moon with no people. The second one goes around with people but doesn't land. Artemis 3 lands. And then that's all that's really been funded officially at this point. But the plan is Artemis 4 through 8. They're buying the boosters for that now, even though they haven't committed to SLS for that. And they're also paying for a new variation on the booster. So there's some R&D in there for developing the new one, which would be used in version 9. They are using up old cases. Those boosters, like I said, they're like in 4 segments in the old boosters. They had the steel for that already because of a similar kind of a contract they had before. So they're just, they had all that steel. Now they're going to finally use it. One interesting thing is these boosters are completely disposable. Back in the shuttle days, the general philosophy was try to be reusable. The part where the reuse failed was that reuse actually was incredibly expensive. I mean, that was true for the shuttle with the tiles and all the other maintenance. It was kind of true for these boosters as well. They did recover them all, but well, except for the ones where they had disasters. But the normal flights, they did recover these boosters. They dropped they had parachutes, and they drop in the ocean, and the boat would go get them. The problem was there's about 5,000 parts on these things because of the engines, I guess, is most of it. And refurbishing them, they had to take them all apart and clean each individual part and do all kinds of work on them. Actually, the conclusion was that was probably more work than just, it probably wasn't worth it to do that. The cost was probably more than just building it and throwing it away. So
we used them 10 times each booster. What someone told me who was associated with the program.
I guess
and then they retired them.
Yeah. So it's interesting. So that they did make reuse work, but it was incredibly expensive because it took a lot of work. Wow. Wait, I can't hear you. There's too much singing going on.
I said if you can hear me, then I have a question.
Yeah.
So for Artemis 4 through 8, if they're getting the boosters for those missions now, and it can be reused like 10 times, like Doug said.
Well, but that was the one that was shuttle days. These boosters are not reusable.
Oh, they're not reusable.
These are not going to be reusable at all. So basically, you're just getting the launches, and that's it. Yeah.
So they just
They just drop into the ocean and they sink, I guess. Or maybe somebody recovers them for scrap metal. I don't know, but it's not part of the plan. Anyway, so in a way, this kind of locks in the technology and it kind of guarantees funding for the vendors. This happens to be Northrop Grumman right now, but that's only because they inherited the program from Orbital ATK, which inherited the program from Thiokol, which actually made the original versions of these boosters. Okay, moving on, space stations. Now, we talked about some of this last time, but now they've made some official awards. NASA is they're spending $416 million to 3 groups. Now, a lot more groups had applied for this funding. I think maybe 10 or more had applied, or maybe a dozen, but 3 of them are now funded. NASA set up a program, which sounds like a pretty good one, a commercial low Earth orbit destinations. It's kind of like the way they did the commercial crew program and so on. Issue a request for a service, and then get people to bid on it. So they're funding it out to 2025. 3 basic teams. There's NanoRacks as heads of one team, and they're working with Voyager Space, which really is just the parent company of NanoRacks anyway, but also with Lockheed Martin. They have this project called StarHab, and that's the one on the left-hand side of this. And we talked about that last time. That is mostly an inflatable thing. So the right-hand side of it in particular is the inflatable part. And there were some questions about this, and the big thing is these things are going to be a whole lot less expensive than the original space station. And obviously, just to get it up there, for instance, this one on the left, they're claiming they can get that up in one launch. This is not, a giant thing like the space station where it takes many, many launches. This is one. Now, all these things are, for the most part, are going to be modular. So you get something up, and if you want to expand it, you launch another module. So they go up module by module. The second team is the Blue Origin team. And again, we talked about that one. Blue Origin heads it up, and that works with Boeing, Redwire, Sierra Space, and others. Sierra Space, they also had an inflatable module. We pointed out last time. That's like this particular one, and sort of the center of this center picture here. Those are the inflatable parts. And again, their initial program would not put up a station that looks like that picture right away. That would be after quite a few modules were up. But the initial modules, would be self-sufficient. One that's new that was not mentioned before and really hadn't been revealed until now is Northrop Grumman is now in the picture, and they got $125 million for that. They're teamed up with Dynetics and maybe some others. And essentially, what they're doing is they're just taking their Lunar Gateway and their Cygnus work. Cygnus was the cargo ship that goes to the space station now. Lunar Gateway, was their space station around the moon. So they're really reusing that work. So they're in the mix. So now there's the 3 of those. Now, one thing we talked about before, there was $140 million already funding Axiom Space, and they're going to have, as part of that funding, they're guaranteed to put in at least one module in the space station, but it's detachable. So that when the space station goes away, they can be off on their own. Now, the one module is not enough for being self-sufficient, but part of that 140 million goes to putting up a total of about 4. And that whole section would actually be detachable. And so they could, they could do whatever they're going to do with the space station, and the Axiom station could stand on its own. Now, this is just funding for R&D essentially. But then, except for, as I was mentioning, Axiom Space, that's actually to put something up there. So they're you can say they're way ahead of the others on that.
Do you know if that 140 is just for building the module? Does it include the cost of launching it, or is that separate?
Which? Oh no, that's including the whole. That's the whole thing, launching it.
Everything. Wow.
Yeah, well, that's including launching the first one. I don't think it includes launching the others, but they have to at least prove they can do one. But as part of it, they're planning on putting up more than that.
Because I gotta imagine it's like 90 million just for Falcon 9, so that only leaves 50 million to build the module.
True. They might be assuming Starship in there. I don't know. I've got to come closer. I can't hear you.
Don't they already have an inflatable module on it?
Well, the Bigelow Aerospace had created this inflatable module. So they proved that you can do it. There is one actually on the space station right now. So no, that was called Bigelow Aerospace. And they went back. Well, they didn't actually go bankrupt, but they just fired all the people. So they're just kind of sitting there. They may yet come back. It's one of those things where they could reactivate that if they get funding. So you never know.
They do have a design for that B330, I think. It'll-
They have a design for what?
Oh, the B330, the bigger module, like the one that's on ISS, Bigelow's is the B module, right? The smaller, like the
Yeah.
astronaut's closet or whatever. Like it's a small.
Yeah, it's up there. Yeah.
But like B330, like the one that's like looks more like its own station, like private space station almost. Yeah, that's not up, I think, right? Or
So you're saying they already have a design for a bigger one.
yeah.
Yeah.
Like,
And- okay, I'm sorry. Yeah, the question was, it goes back to Bigelow Aerospace, and she's saying that they have the one that's up there already. It was kind of a small scale demo. They have plans for a bigger one, and they were already in place. So yeah, one might think they could just go out and try to raise money, and also compete in this area. Because they are the only ones, yeah, you can say that actually put up something that actually works, that's inflatable. Anyway, so all this goes out to about 2025, and then there'll be another round of funding that would actually fund the building of whichever ones get selected. And then there's up to the fun stuff here, SpinLaunch. It's one of those things where, is this a crazy idea that might work, or is it just crazy? And I mean, it makes sense in a lot of ways. What it is, you think about, why does it cost so much to launch stuff to space? Well, one is building custom rockets every time, but once you get past that, another thing is just that it takes a lot of fuel. And the reason it takes a lot of fuel is that when you first get started, most of the fuel you're using is just lifting the rest of the fuel. And so you have a huge rocket, and by the time you actually expend the fuel, there's not much left. I mean, most of the weight of the rocket is in the fuel itself. And so all that thrust is really just going to move most of the fuel. So you want to get past that. Well, how do you get around that? Well, people are talking about railgun kind of things, where you have an electromagnetic launcher where you shoot it up. That's really more or less the same school of thought that this has, except that this one is mechanical. It's not even electrical. What you have is a centrifuge. You just spin basically really, really fast, and you let it go in the right direction. And that's what that would be. So here they have a picture. First, we'll talk about the envisioned one. So this one on the upper left-hand side here, that's not built yet. That's just the envisioned one, but they're searching for a site right now. But I like this one because it shows you opened up. If you look inside, this is with the top removed. So this is before it's completed. There's just a big rotor in there. And the thing you're going to launch is at the top of that rotor in this picture. That's going to be spinning around. Then you have a counterweight, so that it's evenly balanced, and a little shorter arm there at the bottom. So anyway, the thing spins and spins and spins. It goes faster, and then it gets released, and it goes shooting out that chute there. And that's pretty much the basic idea. I mean, it sounds simple. It is simple in that regard.
Is there any sense of human to survive this process, or is this
No.
cargo only?
No, this is yeah. We have to get to this. This is definitely cargo only. People are not going to go on this. It's in the next slide, but you're talking like 10,000 G kind of forces. It's not even just people. I mean, there's nothing organic would survive that. It's strictly for cargo. But the basic idea is you're not even actually getting all the way to orbit. Yeah.
Is there a physics limit as to how high you get it? Is there a physics?
Well, I think the limits are based on how fast you can spin it without destroying it, that kind of stuff.
Yes.
Greg, did you see my
They
message?
claim you can get stuff to orbit almost. But, so what they do is they still have a rocket as a second stage.
Correct.
Yeah,
The highest orbit they could get out of there.
I don't know. I don't know what they've said.
Okay.
Yeah, it's what their plans are. Well, actually, it's on the slide here. Their plans for at least their first version is they can get 200 kilograms, which is 440 pounds, up to low Earth orbit. And that's not all just with this device, though. This device acts as the first stage. It itself doesn't get you to orbital velocity. So you still have a small rocket inside. I'll get to that in the next slide. So it replaces the first stage. So you launch the thing, you send the thing shooting out, and that should save maybe 75% of the fuel. So that's where the big cost savings come in. Because as I said, most of the fuel that's in the rocket is mostly going to accelerate the other fuel that's still left. They're targeting 200 kilograms, their eventual goal is to handle maybe 5 launches a day. So they're targeting small satellites, but that's a lot of the market right now. Small satellites, not people. You know, the one 440 pounds doesn't leave you a lot of room for life support and that kind of stuff anyway. They've raised money to do this, and then they actually did build something. And that's this on the lower left-hand side of this picture, the suborbital test launcher. And this is actually built, it's in Spaceport in America, which is in New Mexico. It's 165 feet high. It's about a third the scale of their final device, which would look like the one above it. And it's going to shoot, it actually, they did their first test, which is why we're talking about this today.
They did a test.
Oh yeah, this has been, well, yeah, that's why we're talking about it today, is because they did actually run a test. And let's talk about that. First of all, a little more details on this. So the rocket itself, that's it there. I think it's like 10 feet or something. It's not terribly big. But this is the thing that gets launched out of the centrifuge, which, by the way, is kept in a vacuum so that they don't have a lot of air resistance. You know, they can spin a whole lot faster. And what's inside that rocket, basically, once it's launched, then the outer, it's almost like fairings here, those come off, and that reveals the actual thing, which has a stage 1 and a stage 2 rocket, all within that 10 feet or so, and then the payload, the 200 kilogram payload up there. And so that's what that looks like. Now, remember we said this thing is kept in a vacuum. That's why they can spin it fast and you not have a lot of air friction and that sort of thing. So what they do, they literally have like a sheet of plastic here at the top of the thing, and this rocket burst just shoots through it.
Oh, okay.
That's how they keep the vacuum. They said this thing was actually even already is one of the larger vacuum chambers that exists.
They needed a really fast door to open up.
Yeah, it's a really fast door. It's called blasting through it, literally. And this is supposed to be a picture from their test. This is what it looked like blasting through. So their first suborbital test, they said it was successful. I'm not sure it was tracked by anybody, so you have to probably take their word for it. But they had video of it and everything. It looked pretty convincing. And I'm saying this the way I am because there were a lot of people that were convinced this was an outright scam, just basically a way to collect money from investors. And I'm not sure we know 100% if that's true or not, but at least they have built something, and it appears they have demoed it. So what they did was they've only run it at 20% power so far. Now you'd think by now they would have run some more tests at higher speed. They haven't yet. And also what they launched didn't contain the rocket engine. It was really just a shell of just a shell. But they said the projectile got up into tens of thousands of feet. So it's got a long ways to go before it gets closer to orbiting. But they're planning on another 30 tests or so in the next 6 to 8 months. I mean, tests are pretty easy for them. You know, they push the button to turn it on. They push the button to say, let it go, and then you see what happens. Now, there are a lot of challenges for this. One is high vibration. The thing is spinning. I forgot, the RPM isn't as high as you'd think, but still, it's pretty high. The G-force is the killer, literally, for people anyway, at 10,000 G. But there's other problems, too. Most rockets, when they take off, they're starting off really, really slowly. And by the time they're going fast and getting significant air friction, they're up way, way high in the atmosphere where there isn't much air. That's the exact opposite here. Here, you're going 5,000 miles an hour when you're coming off the top. And all of a sudden you're going from 5,000 miles, all of a sudden you're hitting this wall of air that wasn't there a second ago. And predicting the aerodynamics of that is probably not an easy problem. You're going to get high temperatures, you're going to get shock waves. So certainly a lot of concern on how that'll work. And that's why they had to do this kind of testing. So at least they demonstrated that at lower power, it could work. Another thing to think about is when that vacuum breaks, you're going to get a sudden inrush of air. That's got to slow you down a little bit. And the other thing is what happens once you release the load, you have this thing spinning, at however many RPM that was. You just released one end of it. All of a sudden you just have you have the counterweight still spinning. I didn't really understand how they solved that problem. They said they have. You shoot it out too.
You have a second mass on that arm that's much closer to the center. And as soon as it swings around and releases the rocket, boom, now you've got that unbalanced arm. You let that second mass run out to the end of the arm, and it takes the place of the first mass of the released rocket. And
yeah, maybe they didn't.
It's the moment arm.
Yeah, it wasn't clear. It wasn't clear how they do it. But even that's not. If you got it spinning that fast, by the time it hits the outer edge of that rotor, it's got to be going pretty fast too. You know, that would be, you know, it's a technical challenge, is what.
About the dense air, what about building it on the top of a very tall mountain?
Yeah, that you have to wonder about that. It's interesting that they picked the. Well, see, they picked up. You can see the ocean in the background there. They're envisioning launching from the coast for the usual reasons for rockets, and that you know anything that falls down is not going to fall on a population. But that's obvious. In fact, well, taking that a step further, places like the moon, that'd be really great because one, you know, it's already a vacuum, and you can just run it, and there's low gravity as well. So you could definitely get to orbit with this. Now, in the past, when people were talking about building O'Neill cylinders and so on, they always said, well, okay, let's just launch a bunch of stuff electromagnetically off a rail gun kind of a thing on the moon. This would be an alternative technology for doing that.
This is a lot better, easier to transport. It's more active.
Yeah. Yeah.
Could we use ISRU to like build one of these?
Okay, so the question was, can you do ISRU in situ research utilization? Could you build one of these things on the moon itself? Because there's a lot of iron in here. There. I would think so. I mean, it probably does take some pretty precision machining at some point, just because you're talking about spinning heavy masses at high speed. You know, you got to be sure the balancing is really good. But you know, yeah, one would think they're not there yet. I mean, they'll be happy to get this thing working on Earth right now. Yeah.
They see how many megajoules of like power it takes to get it spinning.
Did they what?
They see how many megajoules it would take.
Somewhere. I probably saw that in passing. I don't have a number, but it doesn't. You know, it spins up slowly. It takes at least a couple minutes. I mean, it doesn't go instantly to full speed. It takes a while. So, yeah.
I wonder how many launches it can do before like it fatigues the. I don't know how it works, but like before it turns on shoot 100 and then.
Well, the biggest thing is just applying more and more power to see how that works out. The second thing is they have to actually get their second and third stage rockets built. Now, one thing, because of the high G forces and high vibration, they've opted for really simple designs on the rocket. So for instance, that upper stage is really just a pressure fed thing. There's no fancy pumps or anything like that for pumping fuel. I mean, it's just high pressure fuel, shoot it down to be combusted. And anyway, so those are the challenges they have. They don't seem as worried about that. I mean, in a sense, the challenge is, can you make this work? And then, of course, the other challenge is testing. And now they say they've actually verified that there's a lot of equipment that couldn't withstand the vibration and G forces of this. You know, electronics, for the most part, could actually be okay. So
they're saying basically 5 launches a day, spread over like a 10-hour period, I assume, a long day. That would be, they're looking at a 2-hour turnaround time to bring a new rocket in, hook it up to the spinner arm, put a new membrane on their exit tunnel, and then spend most of the rest of the time after that, the next hour, pumping the air out of that chamber.
Yeah, and that in fact may be the limiting factor.
Yeah,
well, that and retrieving these these rocket shells.
The concept is practical, but also be practical.
Yeah.
Not just the one. It would
Yeah.
It would be practical tomorrow based upon gravity.
Yeah.
What would be cool mechanism to replace the plastic sheets? I feel like looks like it's riveted from the photograph. I don't know anything about this, but if they have like the roll of the material and then like somehow there's an arm clips onto it.
Oh, just pull it like a roll of saran wrap. You just pull it out.
Exactly.
Yeah. The comment was, just have a roll of this material, and who knows what they're planning on. This after all is a prototype, but yeah, the idea is, you just have a big roll of this stuff, and once you blast through, you quickly pull out the saran wrap equivalent and tie it down somehow. So anyway, this is a completely different approach to getting into space. I mean, the wilder ideas out there that may eventually really work and be really, really cheap are things like this, some kind of electric railgun kind of a thing, space elevators, those kind of things. When they finally happen, will probably change the economics, even more favorably. But we just have to get past these initial stages.
So when was that first suborbital test? Like,
It was just in the last month here.
oh,
Next topic coming up, launching, I think December 22nd is the current schedule, is the James Webb Space Telescope. Now, Doug is going to talk about that in more depth. I'm just going to give a few quick comments about this thing because it is coming up and it's a big project. This one started back in 1996, so it's kind of been around for a while. The original launch was scheduled to be 2007. They didn't make that. And they still haven't made it, but it's really, really close now. We're almost there, real soon now, as we say. So it would go up on an Ariane 5, that's a European Space Agency French rocket, basically, from French Guiana, which is one of the big launch sites. An awful lot of rockets go up from there. Where it will go is around the Lagrange point L2 for the Sun-Earth system. And there's a diagram there on the left-hand side explaining what that means. So there are several places that are pretty useful for orbiting. Think of an axis going from the sun through the Earth as is shown in that arrow on the left-hand side there. The L1 point is in between the sun and the Earth, and that's where you put things like solar observatories, because the point of that is that for very minimal amount of fuel expenditure, it's almost stable, where it goes the same speed as Earth and it maintains the same angular velocity, basically the same orbital period. And so as a result, it's always in the same relative position to Earth. So for instance, we can communicate, like in the solar observatory case, we can communicate with that always because it's always just in between us and the sun. This is sort of the opposite situation. You actually want to shield this telescope from the sun. So what you do is you put it out there so that it always has the Earth blocking most of the sunlight. You want to see some of the sunlight because you need to get power, but you don't want a whole lot of light. After all, you're running a telescope and you're trying to see things without a lot of light around it. So you want it out there. So L2, that point, again, it matches the period of the Earth, the orbital period of the Earth, but it's further outside of that. And so that's where they're going to have it. But you don't want to have it right there. The problem is that the moon would, the Earth, the sun, the moon, and the Earth, and the sun, they're all in one plane. And that says that as the moon orbits the Earth, periodically it would block a signal path between Earth and the observatory. So instead, what you do is an orbit around L2, and that's called a halo orbit. And that terminology actually came from thinking about it around the moon. If you were standing on Earth looking at the moon and you were doing a halo orbit around it, it would look like a halo around the moon, literally, if you could track, if there was a, like a giant fireworks or something that, left a trail behind it. That's where that terminology came from. But anyway, they are talking about, they are planning on going out to a halo orbit around the L2 point. And so the Earth blocks the sunlight right at the point, but you go around that way you get some sunlight for solar power, and you get, you always have a signal path for transmitting the images. And then Doug will talk about this in more detail. Okay, now we're at that point where we ask, how many launches does everybody think we've had since the last meeting, which was November 6th? And I'll say, I cheated a little bit. I included one launch from China on November 4th in this count. I had to because it wasn't publicly, it wasn't noticed yet back at the time of the last one. So it's one higher than the official period starting on the 6th. And as a reminder, this includes failed launches as long as they got off the launch pad. It only includes launches attempting to go into orbit or beyond. So this does not count, the Blue Origin stuff where we just, send people up and down for 10 minutes. That's not really significant enough to be in this count. The Russian anti-satellite weapon test doesn't count either, because those things, they actually get up to orbital altitude. They have to if they're going to hit something in orbit, but they're not going fast enough to maintain an orbit. So they will never count, in these kind of things either. So how many think there's been more than 12, say, launches in the last month? Okay, how many think less than 20?
less than 20, sure.
Nope, you're all wrong. It turns out there were 21. Yeah, it's been a busy month. All right, so in terms of people's responses, they were guessing like 9. A lot of people guessed 12. 12 was almost always right in previous counts. But, part of that was there were a lot of things that were kind of gummed up because of COVID and everything. And now that we're finally working our way through a lot of that, there's been a lot of launches. Let me clear this out of here. So it's a certain amount of catch-up work going on here. Well, I'm obviously not going to go through all these. I'll just highlight a couple of things. November 10th, there was a third launch of SpaceX, their crew launch to the ISS. On the 13th, there was a new batch of Starlink internet satellites, but this is different because these are at a different altitude. Whereas they pretty much said they've completed one orbital shell where everything, and that was like 320 miles up here. No, it was 340 miles up, a little bit higher than this. So they've completed that one. They're starting a second shell, meaning distance from the Earth. So it's kind of significant in that sense. Astra finally managed to get a test flight going into orbit. They're one of these, these new space companies coming along. They're the ones that are kind of interesting. What?
Where did they launch out?
Kodiak, Alaska.
Kodiak.
They can launch from anywhere. They basically drive up in a truck. They can prepare a launch site in a day or so, and they just they can do it. But obviously, they're doing the smaller satellites, but they've been kind of an interesting one because they have some interesting technologies. I think they were the one that last time I was pointing out that they were the ones that they started to go up, but one of the engines failed and it just kind of drifted sideways for a while. And then finally enough fuel burned up that the thing got lighter and the same amount of thrust was still there. So finally started going up, but it was, by then it couldn't make orbit at that point. They changed their design between then and now. They added basically they added length to it. They put more fuel in the thing. Now it has enough fuel it could go, well, the engines all work for one thing. And the other thing is it has more fuel. So they made the change because of that. So that was kind of interesting. There's more and more of these small companies coming in doing these small launches because there's perceived to be a huge market for small satellites.
And
There is
it's
one.
really incredible that they could identify the problem, identify a fix, and then implement the fix that quickly.
That is amazing.
This is like phenomenally fast.
Yeah.
I mean, this is like NASA in the early 1960s. That's how fast they were going then.
Yeah.
Not since then.
Okay, so we talked about DART already. The Russians put a new module up there. Now that's kind of interesting. They had just recently, earlier in a couple of meetings ago, they just put up the Nauka science module, which was a big one, and that was an old one that had been sitting around. There wasn't enough lift capacity to get up there. They finally put that in there, and they did this one. Now they've really said this will be it. They're not doing any more. All this was basically a docking module. It has essentially it's just a shell with 6 ports on it so that you can hook things up to it, like cargo craft and that sort of thing. When they were, what?
Yes.
Yeah. So it was interesting for a while there, the Russians were talking about not even launching the Nauka module and not launching this one, but taking those two and making their own space station out of it. They changed their mind on that, partially because they decided that that Nauka module had been sitting around so long, they didn't trust it anymore. So they thought it was fine to send to the space station, but they didn't want it in their own space station. And once they did that, they figured, well, okay, they might as well send this thing up and just be done with it. So they've officially said that's it. They're not sending anything more up there. But the plans there was always a possibility that because it has 6 ports, they could easily have hooked in more modules. The other stuff is all kind of routine communication satellites and whatnot. Page 2 of the list, you don't get page 2 very often. Page 2, more of the same. Of course, the one notable one would be the Japanese tourist, the 12-day mission to the International Space Station. That went up on a Russian Soyuz. And this is the same guy that's going to go do the Dear Moon thing, going on the SpaceX craft around the moon when that's available. It's the same guy. He paid for that, and he took a movie guy, somebody with him to make movies out of the thing. The other thing, I underline the fact that there's 2 NASA missions in this current batch. The DART one, I'm sorry, and this other one here, an X-ray astronomy satellite. These are going up on Falcon 9s. It used to be that NASA really didn't send anything interplanetary or anything beyond Earth orbit on Falcon 9 from SpaceX. Now it's kind of become the default. So there's been a noticeable change in that. And that was one of the first.
So you're saying NASA is now utilizing Falcon 9?
Yeah, it's just so much cheaper. It's just so much cheaper that they can't resist.
Yeah,
so
deep missions, deep space missions.
Yeah. Okay. Discussion, questions?
Hold back. So
Yes.
the Any news about the December 7th Atlas V technology demonstration satellites?
I haven't heard much. I mean, other than the fact that it launched. Don't know much about it.
Was it the little midget space shuttle, the X-37 or X-42?
I hadn't heard, I didn't think, no, I thought these were all just routine these satellite kind of demos.
Okay.
There was something special about them, but I didn't actually have time to dig into it.
Okay. So it's okay. There's black sky keeps getting mentioned there.
Yeah, it's another one of these people putting up constellations. These are Earth observation satellites. It's amazing how many there are. I mean, right now they have 12 satellites. Typically, they're selling intelligence to companies or governments. Typically it's just photos, or it could be other other spectrum. But they're doing that. There's another company called Planet that you probably never heard of. They have a couple hundred of these satellites up there doing the same thing. Yeah. There's all these businesses going on right now that almost nobody knows about. They literally have they have satellite constellations that are a couple hundred. This one is nowhere near that big. And there's more coming.
Well, I guess there's a market. I guess the CIA got tired of paying.
It's mostly commercial, but the other thing driving it now is also everybody's worried about climate stuff, so they're monitoring like deforestation in Brazil and things like that, and that's done by taking pictures of satellites. And there's such a market for this.
Well, I think it still does open the possibility that the CIA has not always gotten along all that well with some of the military, and so having to route their intelligence requests through, say, the Air Force to go task this satellite to look at this location may be something that, for whatever reason, they didn't want to share with the Air Force. And now this gives them a second route, alternative route to look at things that are of interest to the CIA, but which they don't really want to share with anyone else at this time.
Yeah. So the comment is that agencies like the CIA don't want to share what they're doing, so they go to these third parties. That's true even more so for foreign governments.
Yeah.
I mean, if you're Mexico or Canada or Israel or something.
Or Sierra Leone.
Or
Ecuador.
Yeah.
Ecuador being worried about possible invasion from Bolivia. I mean, it could happen.
Sure, lots of things could happen. Yeah. But actually, like Middle Eastern countries, they don't have much going on there other than UAE, which has a major space program. But they want intelligence; they can buy it now for American companies.
Yeah, yeah.
If you're Iran, you probably indirectly, you pay somebody else to do it for you, but you probably get it from American companies. They're not all American, but a lot of them are.
I think we're right out of time. We better switch over to.
Yeah. Okay. So
Question.
Doug,
I have a question.
He's been in NSS forever. I don't even know how many years that's been, but forever is a long time. But he's always been interested in space technology. He's an expert in oil field equipment, surface and subsea. He's worked for a variety of companies in that area. I don't think he necessarily changed jobs all those times. I think the company changed underneath him. But he ultimately is a BS in mechanical engineering from Rensselaer and is a licensed professional engineer. And he's going to talk about the James Webb Telescope.